Roger Penrose est professeur émérite à Cambridge. C'est un physicien mathématicien. Je pense sans aucun doute c'est un des plus grands physiciens mathématiciens vivants. À titre personnel, je le considère comme le plus grand. Et il a beaucoup de travaux en relativité générale, mais aussi en rapport avec la physique quantique, des travaux fondamentaux et qui font appel... Il a introduit, je dirais, des idées complètement nouvelles dans ces domaines et des outils mathématiques complètement nouveaux qui sont maintenant très largement utilisés. Et ce qui le caractérise, c'est, outre une connaissance très à fond de toutes ces disciplines, alors que la plupart du temps, on rencontre souvent des spécialistes en relativité ou des spécialistes en physique quantique, je pense qu'on peut dire qu'il domine vraiment les deux domaines. Et les outils qu'il a introduits sont aujourd'hui largement utilisés par la communauté scientifique. Et ce dont il va nous parler aujourd'hui, c'est un des modèles cosmologiques dont il a eu l'idée il y a quelques années, qui est également assez original. Et donc, je lui laisse la parole, professeur Roger Penrose.
No, I stand up, but I can't put this on here. Yeah. Oh, merci. Pardon-moi, je parle en anglais. Excuse me also, because many of the things I wish to say will be difficult to understand. I apologize that tomorrow I shall speak to experts, and I think they will find it more difficult to understand than you will, because some of the things I want to say are unconventional. When I say something unconventional, I will explain that it's unconventional. Now, 1 minute, I have to, how do I move things here? Yes, okay, red and green. Now, the title has to do with Hawking points. Now, that's already unconventional, because in standard cosmology, I shall be talking about cosmology, in standard cosmology, they don't have such things. Now, to tell you what they would look like, if you had eyes that could see microwave radiation, not ordinary light, but microwave radiation, and you were out in space, I claim that you would see certain spots in the sky which are about 8 times the diameter of the full moon. So, not very big, but the full moon seems big to you, but just because we're used to it. But 8 times the diameter of the moon, sometimes slightly smaller, but never bigger than that. Now, these spots are not part of conventional cosmology. However, they are an expectation of the scheme that I wish to describe. Now, first of all, I want to show you a picture of the universe. This is a picture of the universe. It's a space-time picture. Those of you who attended the previous talk will understand about space-time pictures. Time is the dimension going up in the picture. Space is going around. Now, I have to, in order to get the picture, the whole picture in, I have to suppress 2 dimensions of space. So we have 1 dimension going horizontally. In fact, perhaps I will show you the next picture. It doesn't move exactly when I mean it to, but all right. The blue section shows you, roughly speaking, 1 time. So that you imagine that that blue section moves up the picture, and at any one time, you have a section through this picture of the universe. As you see at the bottom, let me go back. I have to get used to the time, do I? Yeah. Oh, no, that was meant to be backwards. I was told that if I press the red button, it goes backwards, and the green button, it goes forwards, but it doesn't seem to do that. Okay. Yes, so the Big Bang is at the bottom. That's supposed to be the beginning, and then the universe expands outwards, and as the time progresses, it slows down in expansion a bit, and then it starts to accelerate in its expansion. This is a fairly recent discovery, this acceleration of the expansion, which is often called the effect of dark energy. I call it the effect of Einstein's cosmological constant, which is a term that Einstein introduced into his equations for general relativity for the wrong reason. He wanted a static universe, but when it was found that the universe expanded, he retracted his cosmological constant. It's called the lambda term. But unfortunately, or fortunately I should say, that his introduction of this term does describe the way the universe has this expansion in the remote future. Now there's another feature of this picture which may seem puzzling. At the back, it's sort of got frilly. That's because I don't want to prejudice the issue as to whether the universe actually closes up and is spatially closed, or maybe it is open and it goes and does complicated things. So I'm not going to be concerned with that, except that I shall describe the three... I'm sorry, there is a time delay in my... I want the next picture. Perhaps if I say, next picture, please. This thing doesn't seem to do much. Next picture, please. Yes. Now, you see, these are some pictures due to the Dutch artist M.C. Escher, and they describe the three types of uniform geometry. At the top left, we see a picture. These are all in terms of angels and devils. It's very clever how he does it all. In the top left, we see the ordinary Euclidean geometry, which is a flat geometry. At the top right, we have the positively curved geometry, which you can think of as the surface of a sphere, except that you have to think of more dimensions. This is only a two-dimensional geometry. In 3 dimensions, it's a similar thing, but one more dimension. But the positive curvature is the one at the top right. The one at the bottom is the picture of negative curvature. That is the third kind of geometry. Cosmologists tend to believe it is more or less flat, the top left one. However, it doesn't make much difference, and what I want to say, we don't care too much which it is. But the reason I have the frilly geometry at the back is just so that I don't want to prejudice the issue. The picture at the bottom will have importance for us later on, and I'll come back to it. Now, I want to move to the next picture, if I may, which I should talk about it if I could remember what it is. It's just the one we just had. So this is our universe. Now, I want to say something about the Big Bang. Some people would say this picture is inadequate because it does not describe the very early stage of the universe, which is called inflation, or cosmic inflation. Now, there are 2 reasons why I don't describe it in the picture. One of them is that perhaps I do, because it's really in the little point at the bottom, completely squashed up into that point, and you would not see it. The other reason it's not in the picture is that I don't believe it. So this is one thing which is different from standard cosmology, is that I don't believe in the initial inflationary phase. Now, I want to show you what inflation looks like, if it is there. We need a very powerful magnifying glass to have a look at it properly. And the next picture shows you what you would see. You would see something which looks very like the remote future. It has this exponential expansion, which is what we are, again, beginning to see on a completely different scale in the remote future. However, there is supposed to have been such a phase in the very early universe. Now, what I'm going to claim is that there was not such a phase after the Big Bang, but there was, in a certain sense, such a phase before the Big Bang. So inflation is needed to explain certain features of this radiation which is coming in, the cosmic microwave background radiation, which is microwave. And this is in this radiation, I claim you would see these spots, which are 8 times the diameter of the moon, slightly warmer than the temperature all around. People don't... Why have they not seen this? Well, the reason is nobody looks. And the reason nobody looks is because they believe that inflation irons out the universe and makes it uniform. I'm going to claim that it's not as uniform as we think. Now, let's go to the next picture. The next picture is the same picture I had before, but with time going the other way. I'm going to try and explain why I don't believe that the universe makes the inflationary phase makes the universe uniform. I don't think I should spend too much time on this because I don't have a great deal of time. But you see, so let's suppose that the universe was collapsing and we had the inflaton field, as it's called, which explains inflation. You put it in, and now I want to make it a little irregular. I'm going to put irregularities in it. Inflation is supposed to get rid of the irregularities. Let's put them in, and what happens? They produce black holes. These black holes all congeal into a great mess. And that would be the most likely kind of ultimate future of this universe, with the inflationary field or not. Now, if we now consider that the other way around, now this is the much more likely initial state, the universe was not like that. And inflation, the inflaton field, would not iron out this initial mess. Why was it not like this? Well, I want to try and explain something about that. But it's not like that. It's much more like that. This is very much like the picture that we really see in the universe. Now, I want to say now something about, this is an Escher picture, not quite the same one I had before, but it is another Escher picture describing the same kind of geometry. Now, this is a picture in what's called conformal geometry. Now, in geometry, you're used to thinking of just distances. It may be a curved geometry where the distances are not uniform, but on the other hand, we think of distances. Now, there's a more general kind of geometry, which is called conformal geometry. Now, conformal geometry is the geometry of angles. So if you have a triangle, the triangle will have certain angles, and you can have a big triangle and a small triangle, and the geometry I'm interested in is the geometry of the angles of the triangle. Now, you can have a geometry which is not like Euclidean geometry, and this is the one we're describing here, the negative geometry. But the point I want to make is not that this might be the geometry of the universe. I'm not sure it is. It's not, I don't expect it to be necessarily, but it illustrates a nice feature. In this kind of geometry, you can represent infinity. You see, infinity is that circle around the outside. And you see that the little fish, or whatever they are, that very, very small, but they think they're just the same size. In the geometry being described, the white ones and the black ones each think they're exactly the same size and shape, no matter how close to the boundary they are. But from our perspective, we can do a conformal map which squashes the whole picture down so that infinity is represented by a finite boundary. Now, this is a very useful trick in relativity, and I'm going to use this trick in space-time, not just in this two-dimensional space, but in four-dimensional space-time. Now, in order to describe the geometry of space-time, it's really best to talk about the light cones, or the null cones. You see, in the top picture, on the left-hand side, we have a light cone, or a null cone. And this describes a flash of light. So you imagine at the vertex, that little point in the middle, suppose there is a flash of light. On the right-hand side, you see a spatial description, and that one has all the dimensions in it. On the left-hand side, I had to throw one of the dimensions away, and as the light goes outwards, first of all, it's a point in the middle, and then it reaches the red sphere, I think it's red, and then the blue one. I can't see the colors very well, so you'll have to correct me on that. The blue one on the outside, and those are sections through the cone on the left. So the cone, I have to throw one dimension away, but it really represents what you see on the right-hand side. It's the history of a flash of light. Now, the history of the flash of light has a bottom part to it, the inward cone, and that is of light coming in, focusing at that point. Now, this tells you most of the geometry of space-time. If you know where those cones are, you know most of the geometry of space-time. Now, special relativity, which I think the previous talk was about, mainly, special relativity, you just see the cones are uniformly distributed. In general relativity, they can be sort of all over the place, one way or another. The important thing is that light, a flash of light, or a particle of a photon of light, is described by a line which is along the cones all the time, whereas a particle, a massive particle would always be within the cones. And that's the important part of relativity. You can't travel faster than light, but your world line, that is the history of a point, would be within the cones. Okay, so that is the main part of the geometry. And what I'm trying to say, that is the conformal geometry. It's not quite all the geometry. Now you see the top picture, I have on the left-hand side the two most famous formulae of 20th century physics. One of them, the second one I think, is Einstein's E equals mc squared. That tells you, c is a constant, it tells you that E, that's energy, and mass are equivalent. So energy and mass are equivalent. The top formula is even older, the beginning of 20th century physics, of quantum theory, was Max Planck's formula, E equals h nu. Nu is a frequency, that's the Greek letter nu. H is again a constant. So it tells you energy and frequency are equivalent. So if you put the two formulae together, it tells you mass and frequency are equivalent. So if you have a massive particle, a stable massive particle, it is a clock. It's a fantastically accurate clock. And a lot of the amazing things you can do in physics these days depends upon that fact. The fact that we have so precise clocks ultimately depends on the fact that mass gives you frequency. So that's the top picture. The bottom picture is telling you what would happen. You see, I've introduced, in addition to the cones, what mass gives you, and it gives you how clocks behave. So I've got two clocks whizzing through the point of the, you see, imagine you have two clocks whizzing past each other, very close to each other at that point, and they're identical clocks, but the first tick is represented by the first little bowl-shaped surface. The second tick is the second surface. So we now have the geometry of space-time if we don't just have the cones. I should say the cones, in order to describe the geometry, you need 10 numbers per point. The cones are given by 9 numbers. That's really the ratio of those 10 numbers. The 10th number is the scale. Certain things in physics only need those 9 numbers. Certain things need the 10 numbers. The difference is, if you have mass, then you need the 10 numbers. If you don't have mass, you only need the conformal geometry. You just need the light cones. You don't need the scale. And a lot of physics doesn't need the mass. And the main part of physics which doesn't need the mass is light. Photons have no mass, and in the bottom picture you see a photon going along the cone. It never even meets the first cone, the first bowl-shaped surface. So that the photons don't need the mass, they only need conformal geometry. So this is an important point in the diagrams that I want to describe to you. Now here is a little trick. It's just a trick, but it's an important trick. What I've done at the top is, like the picture we just had, the Escher picture, I've squashed down infinity so that it is a boundary. So the purple line on the left, well, it's at infinity, you don't see it. But on the right, I've squashed it down, just like in the Escher picture, to be that boundary at the top. So I've squashed infinity down, and as long as we're only talking about things without mass, it very well describes the physics. Now, in the remote future, the most of the particles that will be around, by a huge factor, will be photons. And the photons, we see the picture that I described here came about because I was worrying about the future, you see, and I'll explain a little bit about why I was worrying about the future. That comes on later, but let me talk about the beginning too. The Big Bang, I've done the opposite trick. I've stretched it out, and that is another boundary. So there's nothing unconventional about this picture. It's not usually drawn this way by cosmologists, but it's a perfectly reasonable way to draw it. Now, the point I'm making here is in the remote future, we have things with no mass, and so even the physics is pretty well described by this picture. And in the past, it's the other way around. You see, in the remote future, you have it very cold, very rarefied. In the remote past, in the Big Bang, it's the opposite. You have very, very hot and very dense, but in a certain sense, they're very, very similar. And if you didn't have mass, they would be extremely similar. And that's the important point I want to make. Now, you see, why do I say that in the remote past, near the Big Bang, it's good enough to ignore the mass? Well, it's a different argument. There, things get so hot everything is moving around so fast that the energy in their motion is much greater than the energy in their mass. And so the particles are described very well by a particle which has no mass whatsoever, because the mass that it has is completely swamped by the energy in its motion. And so again, you can legitimately describe the physics by things with no mass. And so the picture is a good physics picture too. Now, I want to elaborate on this a little bit. First of all, in the past, now, you see, why does the picture not have that great mess which I described? That's a much more likely thing to be the beginning of the universe. Why do I say much more likely? Well, if the universe was chosen at random, it would be like that great big mess at the beginning, not just like the very nice smooth picture that we seem to see. Now, this is a feature of the second law of thermodynamics. Now, what does the second law of thermodynamics say? It says that randomness increases. Well, it's called entropy, which is roughly speaking a measure of randomness. And it tells you as that time progresses, randomness increases. Now, this then tells you that if you go back in time, the randomness should be very, very small. So the universe was not random. Now, this is a thing that people have trouble trying to come to terms with, and they try to make inflation get rid of all irregularities. But it doesn't. And I tried to say that in the earlier description. I don't think I should say any more about that much, but let me say something about this picture up here. Now, you see, as you go back and back and back in time, another way of saying the second law is that if you go backwards in time, things get less and less random. The entropy goes down and down and down. Now, what's the earliest thing that you can directly see? That's the origin of this microwave background, this radiation which is coming in all directions. It was discovered, it twice got the Nobel Prize. Once it got the Nobel Prize for its discovery. Secondly, more or less got the Nobel Prize because of this picture here. This picture is describing more detail what the radiation is like. It's telling you the bottom, we see the horizontal line at the bottom, the x-axis if you like, is the frequency, and the y-axis going up is the intensity. And that tells you what you see in this radiation. And then you see these lines which are error bars, and these are exaggerated by a factor of 500. So you must consider that the error bars are hugging that incline. So it's a very good picture of what that radiation is like. Now, there's a bit of a paradox there, because what is this a picture of? This is the famous Planck curve, which describes, well, maximum entropy. It tells you what a state of maximum entropy, what radiation and matter in equilibrium with each other, the radiation would follow that curve. So what do we see? You go back and back and back in time, the entropy should be going down and down and down until the first point that you ever see, the entropy is at a maximum, because this curve is telling you it's at a maximum. And that seems like a paradox. I regard that as the mammoth in the room. Why don't cosmologists worry about that? Because it should be a state of very low entropy, whereas you see a state of high entropy. Now, it's not a paradox. Why is it not a paradox? Because what we are seeing is radiation and matter in equilibrium, and that's fine. Okay, the universe is expanding, but that's a minor point. That's not the point of the argument. The point of the argument is that what you're not seeing in that picture is the entropy being low in gravity. And this is a crucial point of the picture. Now, you see here, the top picture here, I just have a cartoon. Suppose you have a box and you have a gas in the box, and initially it's tucked up in the corner, and you remove the partition, if you like, and the gas then spreads out. So uniform state represents high entropy for a gas in a box. Now, what about the bottom picture? Now, these are gravitating bodies. You imagine, say, a galactic scale box, and these are stars or something. And then you see, you could start off with a uniform state, and as the entropy increases, it gets more and more clumpy. So what you're seeing in the universe is a combination of the top right picture and the bottom left picture. Uniform sky. This indeed is what you see. This microwave background is extremely uniform over the whole sky, which is consistent with low entropy in gravity, and high entropy in matter. And that is what we see. So the puzzle that we've got to explain is why was gravity not why was it sort of aloof to all this raising of entropy? Okay. Well, you see, it's important too how we live, because you see, we live off the sun, and people say we get energy from the sun. That's not really correct. Schrödinger was the first, I think, to point out what we really get from the sun is energy in a low entropy state. The sun is a hot spot in a dark sky, and because of Planck's formula, the energy comes to us in a small number of photons, and it goes away in a large number of photons. I don't want to talk about that picture particularly, but it's an illustration of we're living off the fact that the universe has condensed, and the matter in the universe is condensed into these hot spots, which are stars, and that's what we live off. That's how we our entropy is kept low because of the sun being a hot spot in a dark sky. So, okay, this is consistent with the picture I've shown you here, that the gravitational degrees of freedom are not excited. They're very uniform, and one way of saying that is in this picture. I had another complicated way of saying, which I won't describe to you, but my former student, Paul Todd, had a much better way of saying it, and that is just this picture. It's saying that conformally, you can stretch out the Big Bang and make it a nice, smooth boundary. That's not unconventional. It's not the way you usually hear it from cosmologists. It's a picture of the way the universe is. That's not unconventional. What is unconventional is my next picture. What I'm saying is that our eon, you see the one in the middle is meant to be us. That's our universe. I'm not calling it our universe, because our universe, I'm saying, is this continuing succession of eons. Our eon started with our Big Bang, and it will finish, in a certain sense, by this exponential expansion. And when we stretch out our Big Bang and squash down our remote infinity, we find that it seems to fit very well. The squashed down remote future does seem to fit very well to a stretched out Big Bang, with this very special condition that the universe was very uniform. And it gives you that. If this model is correct, then you have an elimination of all those very messy, complicated Big Bangs that might otherwise have taken place. So it's a very nice model, I think. And this is what I want to try and describe to you. So this universe, the universe consists of a succession of eons, each of which has its own Big Bang, each of which is very nice uniformly Big Bang, which is the continuation of a previous remote future. As I said before, they don't look very much similar if you think of the geometry which involves distances and mass, because you have a very hot, dense initial state in the Big Bang. You have a very undense, very rarefied, cold remote future. But from the conformal point of view, if you squash down the cold universe, it gets hotter. If you stretch out the hot universe, it gets colder. And so even the physics matches very, very beautifully. Now I want to say something else, which I've not described as yet, which is an important feature about the remote future, and that is black holes. It's very important because it's where all the entropy goes in the remote future. This is a picture, a space-time picture of a black hole. People usually represent it by a black blob, which doesn't tell you very much. But if you put the light cones in, you really see a lot of what's going on. I'm not going to spend too much on this picture, but you see the cones tip over in such a way that they become, the outer side of the cone becomes tangential to this cylinder at the top. That is the event horizon, and you can see that a particle which falls in gets trapped and it cannot escape. So this is a conventional picture of collapse to a black hole. Now what happens to black holes in the remote future? What happens is, well, this is, first of all, I put the black holes in the picture now, so it's not really to scale now anymore, but never mind. Those are now the lines representing the singularity. As I should have said, that the Big Bang is considered to be a singularity where curvatures go infinite, and the black holes have singularities in their middles, which is where curvatures go infinite. That's where I mark things in red. But never mind too much about that. Now, what happens to the black holes? Well, according to Stephen Hawking, if you wait long enough, then these black holes will start to radiate away. They will radiate away. To get a picture of this, there are a lot of black holes which are very, very big, supermassive black holes. Our galaxy has a black hole in its center which is about 4 million times the mass of the Sun. It's a relatively small one from some other galaxies. There is the Andromeda galaxy, which you can see in the night sky. The Andromeda galaxy has a black hole which I think is about 40 times bigger than ours. Never mind. The biggest ones which we seem to see, how long would you have to wait? You see, the universe has to expand and get colder and colder and colder. This radiation is very, 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 very cold. If you have to think of the hottest temperature you ever get in these things, you have to compare it with the coldest temperature ever made on the Earth. But when the universe expands and expands and expands, it gets very, very cold. And then the black hole becomes the hottest thing around, and then it evaporates away by Stephen Hawking's black hole evaporation. Now, the biggest ones, actually probably not the biggest ones, it would even be longer than this. But how long would it be? Think of a googol years. What's a googol? It's not a very scientific term, but think of 1 followed by 100 zeros. That's a googol. You write it all out into an ordinary notation, that would be a googol. Now, if you wait that many years, some of these supermassive black holes will have gone off, bang, pop, or whatever it is. Some of them won't have. They take an awful long time. But we're talking about infinity. Infinity is a lot longer than an awful long time. So these things will all disappear. Now, the crucial point about this in my picture is that although that radiation spreads out and spreads out and spreads out, if you remember that picture, I don't know if I've got it here. You see, I've got them going off pop here. The actual final disappearance of them is a relatively boring thing. I called it a pop. Okay, you can think of it as a nuclear explosion or something, but cosmologically it's really very, very trivial. Almost the entire mass of that black hole, which could be the entire mass of a galaxy, it probably will ultimately be the entire mass of a cluster of galaxies. Galaxies tend to be in clusters. Ours is a relatively small one. There are lots of bigger clusters of galaxies out there. And their supermassive black holes will finally swallow each other up. We are in a collision course, our supermassive black holes in a collision course with the Andromeda galaxy's black hole, and they will spiral at each other, and there will be some explosion when that happens. I'll say a little bit about that, but I want really to talk about the Hawking effect, which is really what I'm talking about. So let me go to the next picture. You see, can you observe? I used to talk about this thing, and I'm thinking that there's probably somebody telling me how much time I have left. 5 minutes, is it? Thank you. I used to think, I gave lots of talks for a while, and thinking that nobody will ever be able to prove me wrong, so I can talk about this forever. However, I then began to think of, well, maybe there are observational effects. Now, this picture is showing you one of them. These are a collision between supermassive black holes. The horizontal plane in the middle is the join between the previous eon, which is before that thing, and our eon, which is above it. And this is us right at the top. Looking back, that's our light cone, and seeing the effect of supermassive black holes in the previous eon colliding. And I'm not really talking about that, but this is a picture of my colleague Valhi Gursajan plotted out lots of these things in the sky, and they form a very uniform, non-uniform distribution. You see these things in the sky. Nobody believes me because the sky is not to be, you're not supposed to see irregularities like that. A Polish group headed by Krzysztof Meissner, Paweł Nierowski, and another Pole, and subsequently a Korean called Daniel An did some analysis. This is I should say the first one was the Planck data, the WMAP data. That was one satellite sent out. This is a more sophisticated satellite called the Planck data, and you see that it's still very, very non-uniform. People didn't like that because they didn't like the non-uniform. I didn't want to go too ahead. Can we go back just for a second, please? That one showed the concentration of the centers. Well, let's go on to this picture. Now, this is now something else. Now, below that plane, you see the bottom, the red plane is the crossover between one eon and the next. So we're seeing supermassive black holes finally evaporating away, and you have to imagine that Google years, if you like, but remember the Escher picture I showed you? Right up on the edge, you see those angels and devils, or the fish, or whatever they are, get very, 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 very tiny. So that everything that happens, even though it's a long, long time, is squashed into a tiny point. So the supermassive black hole, the entire radiation of that supermassive black hole will be concentrated into a point. And we now, this Vahi Gozayan and I, by using one method of analysis, and the Polish group using another method of analysis, seem to see these points. Now, it's mainly the Polish analysis which I'll talk about because they give a figure to it. They looked at, first of all, at the WMAP analysis, and they found a confidence level that this is a real effect of 99.4% confidence. Now, they looked again. This is perhaps a good picture of, let me just explain what I was just saying a minute ago. They looked again, and they found these Hawking points with a 99.98% confidence. So it's pretty clear they're there. They are seen both in the WMAP and in the Planck data. The 5 most prominent points are in exactly the same places. This picture is just to give you a cartoon. The bottom line is the crossover between the previous eon and ours, and you see the Hawking, the evaporating black hole, producing a big explosion. As all the energy in that black hole's radiation comes through, it spreads out. The next line is what you see. That's the cosmic microwave background. That is 380,000 years after the Big Bang. And a point spreads out to 4 degrees in the sky. So when you see these spots, which are 8 times the diameter of a moon, that is what you see. That's you looking back, you see not the point, the Hawking point is the point at the bottom. What you see is the spread out spot out to 4 degrees in the sky, which we claim is the result of a Hawking point. Now, maybe there's some other explanation which somebody will come about, which tells us, you see, you can't have inflation in this picture. It would spoil the whole picture. It would have to be explained in some other way. I haven't heard of any other explanation, so I'm leaving you with this. This is what I'm claiming we are actually seeing. We're seeing the spread out in the 380,000 years where a point at the Big Bang becomes what you see in the microwave background, spread out to 4 degrees. Thank you very much.
Thank you very much.
Okay. Well,
Sorry.
shall I move out of the way?
Sorry. Désolé, on ne va pas avoir le temps pour les questions. Donc je passe tout de suite à la synthèse de cette conférence. Alors d'abord, vous savez qu'aujourd'hui la majorité des cosmologues s'accordent à dire qu'après le Big Bang, l'univers aurait connu une phase d'expansion phénoménale, donc qui s'appelle l'inflation cosmique, pendant laquelle ces dimensions auraient cru de façon considérable. Mais vous, Roger Penrose, vous ne croyez pas à ce modèle de l'inflation cosmique et vous proposez un scénario très différent pour notre univers qui concerne à la fois le début de notre univers, mais aussi la fin de notre univers. Et ce scénario s'appelle CCC, la cosmologie conforme cyclique. Alors l'idée fondamentale, c'est de dire que la phase d'expansion de l'univers accéléré s'identifie en quelque sorte au Big Bang de l'univers suivant, donc à la naissance de l'univers suivant, univers que vous appelez éon. Et donc notre univers en quelque sorte se régénérerait en permanence, d'où l'idée de cosmologie cyclique. Alors comment est-ce possible? Il y a une justification physique et une justification mathématique. Je vais vous donner la justification physique de façon très simplifiée. Donc on parle d'âge très avancé de l'univers, on parle de gogol, en l'occurrence vous avez cité le terme, un gogol, donc c'est un 1 suivi de 100 zéros années. Donc dans des âges très avancés de l'univers, toute la matière va finir par s'agglutiner et par être capturée par des trous noirs. Et ces trous noirs donc vont absorber tout, à la fois la matière et le rayonnement. Et pendant ce temps-là, la température de l'univers, donc qui est actuellement de 2,7 Kelvin, va diminuer. Et tant que la température de l'univers reste supérieure à la température des trous noirs, les trous noirs vont être chauffés en quelque sorte, mais il va arriver un moment où même les trous noirs les plus massifs, donc les plus froids, vont eux-mêmes devenir plus chauds que la température moyenne de l'univers, et dans ce cas-là, les trous noirs vont commencer à s'évaporer par un rayonnement bien connu, donc le rayonnement de Hawking. Et ils vont émettre en fait essentiellement des photons, donc des particules sans masse. Et là, il va se passer quelque chose de tout à fait remarquable, c'est que l'univers sera constitué uniquement de particules sans masse. Et je vous renvoie à la présentation précédente de Roland Lehoucq, où en quelque sorte, on pousse dans cette expérience de pensée le paradoxe des jumeaux à l'extrême, puisque dès lors qu'une particule est sans masse, elle se déplace à la vitesse de la lumière, et donc en quelque sorte, elle devient immortelle par rapport aux particules qui auraient une masse. Mais donc là, on se retrouve dans un univers qui est constitué uniquement de particules sans masse, donc de particules qui se déplacent, si vous voulez, sur les bords des cônes de lumière, et donc cet univers peut être décrit par une géométrie bien différente de l'espace-temps de la relativité générale. Et cette géométrie, c'est donc la géométrie conforme. D'où l'idée de cosmologie conforme cyclique. Alors, l'idée de ce passage d'un univers à l'autre, c'est qu'on peut mathématiquement, c'est la justification mathématique cette fois, décrire le passage d'un univers à l'autre grâce à cette géométrie conforme par des transformations un peu particulières, des changements d'échelle qui permettent donc de passer d'un néon à l'autre. Et puis on peut se représenter cette géométrie grâce à l'œuvre d'Escher, qui permet notamment de représenter l'infini dans une bordure finie. Alors, le problème quand on élabore une telle théorie, c'est de la soumettre à l'expérience. Et plus précisément, dans ce qui nous intéresse ici, c'est la question cruciale est, est-ce que l'éon précédent, donc l'univers qui nous a précédé, peut laisser une trace dans le nôtre? Et pour répondre à cette question, plutôt cette demande, disons, de la physique, vous proposez en fait une analyse du fond diffus cosmologique, donc, qui a été découvert en 1964. Le fond diffus cosmologique, donc, c'est en quelque sorte la signature du Big Bang, le rayonnement fossile, autrement appelé, qui est apparu quand la lumière a pu se libérer de l'emprise de la matière. Et donc, ce fond diffus cosmologique se comporte comme un corps noir de Planck. Et l'idée fondamentale, c'est qu'on pourrait trouver dans les fluctuations de température de ce rayonnement qui est globalement très homogène, des indices de l'existence d'un univers, d'un néon précédent, et plus exactement d'un phénomène bien particulier que j'ai évoqué, donc l'évaporation des trous noirs à la fin de l'univers précédent. Et donc, il y aurait potentiellement dans ce fond diffus cosmologique des points de Hawking qui font, comme vous l'avez dit au tout début, 8 fois le diamètre de la Lune, qui sont actuellement inexplicables dans le cadre de la cosmologie conventionnelle et qui peut-être trouveraient une explication donc dans le cadre de la cosmologie conforme cyclique. Ces points sont donc appelés les points de Hawking, en hommage à Stephen Hawking, que vous avez bien connu. Voilà, et puis donc je termine en signalant que Roger Penrose sera en dédicace, donc n'hésitez pas à aller le voir. Merci beaucoup.